Alrighty then. All right, we have a clap. There we go. All right, guys, what's going on? Memes here. Yes, I know. Late as per usual here. But, I see you, Rick and David. We'll get there in just a moment. We're just starting the broadcast. Let folks from different parts of the internet creep on in. Or chill, or comment, or do all that little jazz here. But, we'll lay out what today's talk. Okay, so there's some stuff on the board from yesterday. Let's see. We already took a picture of all that. Basically, Pascal's triangle. If you have E and you set a matrix to that and that, then apparently you get Pascal's triangle and you have it diagonalized. Apparently that's supposed to be a thing, very beautiful and everything. But that's not why we're here today. Why we're here today is actually thanks to I'm going to give credit, shout out to Rick here, because Rick had made a comment the other day. He's like, the plank time, the plank length are building blocks. So I'm like, all right, Rick is a smart dude. Let's look at them like building blocks. And then I do a little calculation and I'm like, what's that doing there? I was not expecting that, because you do it. We'll get into the actual calculations here in a minute here, but I'm just going to lay out basically my shock as I'm going through, and I do this calculation far too late at night, and I'm like, okay, I have no idea if this is trivial. Everybody already knows this. It's duh, or it actually has some impactful significance. For me, I'm very biased. I would love to think it had impactful significance, or even if it's just duh, it at least helps me as a dude on the internet to try to be able to better parse and understand some of these different calculations and everything, and some of these different relationships between the constants of nature and our reality as we know it. Okay, so what exactly am I talking about here? Well, apparently, as Thad, Rick, and John Williamson have all stressed to me, when you look at things inversely, perhaps they tell a different tale. So, all right, we did take a picture of this. So okay, here's what we're going to do as I'm erasing it. So basically, if you just do 1 over c squared, you get a very interesting number. It's like 1.11-ish times 10 to the 17 kilograms per joule. And I'm like, wait a second. This number looks very familiar. It happened to be the number that I needed to set it equal to in order to solve for at least what I would claim as the vacuum energy density, which basically you're solving for your x term when you set it equal to, and then you're taking the geometric mean of that number combined with the Planck mass or Planck energy or however else out you want to get those numbers there. And I'm like, well, of course it's familiar. I'm on Kodat. I was looking at before. I'm solving like 14 significant digits and everything. I'm like, well, this should be a duh. But I just knew it as the relativistic mass of 1 joule. But I'm like, wait a second. It's literally the c squared conversion. It literally is the mass energy equivalent of c squared. And I'm like, that's very interesting. I never thought of it that way before, but yes, Rick, I am a total creeper. But oh yes, welcome nerdy, the rodent wizard himself. And I'm not talking about, oh God, he's the New Hampshire Libertarian. No, Vermin Supreme. He often runs for, I don't even know what and everything. And he wears like a boot on his head. I guess he's the New England equivalent of whatever that Dark Knight that always, Lord Buckethead, I think, from the UK, who runs in the elections and occasionally gets a not insignificant amount of the vote. I might just be making that up. I'm not a UKer, so I couldn't comment much on that. But see, I can never finish anything. I'm just going through here. So what the heck are we talking about? All right. So what we're talking about is this little thingy here. All right. So Rick mentioned the other day, time and the length are building blocks. So I did something this way. we'll skip ahead to actually what it was. So I took the Planck time, small t, sub p, divided by the Planck length, L sub p. Yes, for those that have been following, we're doing the exact same thing we did to get the simplified fine structure constant. We're taking a thing, dividing it by another thing, and we're squaring the whole damn thing. Why? Because we can, and what it gives out is, it's basically 1.113, I believe, times 10 to the minus 17. That's kilograms per joule. Okay. I'm like, wait a second. It's basically the relativistic mass of 1 joule. Now again, maybe I shouldn't be surprised at all. No, that's the standard energy conversion rate. Yada, yada, yada. It is literally c squared. I'm like, well, I guess duh. No, actually, technically it's the inverse of c squared for this. And then if you multiply it by 1 joule, then you get kilograms. And then if you divide by kilograms, if you divide by kilograms, you'll end up just getting the relativistic energy in joules there. But why should this be surprising in anything? Again, I'm sure plenty of folks know it. You have this like numbers and everything on co-data, but at least for me, the other reason why that was important is just for anybody new that may be joining us, if you want to get alpha, as it is defined, you can either do this whole thing over here. You can do the elementary charge squared. You can do it over 4 pi h bar c, the speed of light, and then E naught, the electric constant. Okay, you can do that. That is also equal to elementary charge over the Planck charge Q sub P. Square the whole thing. Okay, so alpha, aka the fine structure constant as we know it, is equal to this whole dang thing or this thing. Seems to be a computational equivalence, if you would. How very fascinating. And that's why I'm showing that. And again, I'm sure plenty of folks have noticed this before and everything, but yes. 1C. I like that. Yeah. Yes, the 1 is silent. We often don't think of the 1, but there's a 1 there. Yes, Rick, I totally agree. Yeah. 1C squared to the minus 2. C to the minus 2. So we can do that. Yep. All right. Bone is joining us in cat form today. It's good to see you, my friend. We're just talking about stuff and things, and it's like, all right, wait. So what is a joule? Okay, so I should probably also say what is a joule? Joule is energy. All right, so you get Joule. The name of, I believe, was it something Prescott Joule. He was a doctor, probably a professor or something. Worked a lot. To be fair, I have no idea. I just know it's named after something Prescott Joule. And that's basically just energy. So, energy. I think even I can spell that. Started following, was it the Department of Nuclear Energy or something the other day. And they're like, here's the thing. Did you know that with 1 pellet of like uranium, you get the equivalent of like 100-something barrels of oil? And you'll get like, or maybe gallons or something like that. I have no idea. I remember back in the days, they said 100 barrels of oil or 1 ton of coal or X amount of natural gas. It's like, yes, get rid of these things. Because remember, you can hold uranium in the tips of your fingers. And I'm just sitting there and I'm like, I understand the point. But rather having a picture of like some fingers out there like holding your uranium pellet and stuff like that. Listen, I understand OSHA might be like a pain in the butt and everything, but do you really think it's smart to have the actual government account that's yes, it's hip to be square. Do you think you should have the government account out there saying, yes, you should use nuclear power? Why? Because with 1 gram of uranium, you can hold in your fingertips literally the equivalent power of all this stuff. I'm like, Now, maybe you want protective gloves or something just because uranium tends to be radioactive and stuff like. I understand. It's supposed to be like an alpha emitter, so like piece of paper, some lab protocol. I'm sorry, I had to roast them a little bit there. I understand. I get their point. But all right, the actual point of what we're talking about here. Let's see. Okay. So the point here is, all right, we've got our window over here, this guy. All right, so we'll share with the class here. All right, so what am I talking about? That whole thingy right here. All right, Planck time over the Planck length. Yes, that thingy that we had on the board over there squared. We get this number. 1.113 times 10 to the negative 17 seconds squared divided by meters squared. Again, doesn't mean a dang thing to me. And Wolfram Alpha happens to tell me, oh, that's kilograms per joule. And I'm like, WTF, mate? Mass per energy. Oh, that's just a conversion. The C-squared conversion. Oh my God. Yeah, because if you multiply it by a joule, so we get the joule out of the denominator. You get a mass term. That gets out the mass term. Yep. 10 to the 17, negative 17 kilograms. Blah, blah, blah. All right, about 11 femtogram, aka the relativistic mass equivalent of 1 joule. Oh, wait a second, 1 joule? And that got my noggin a-jogging. I'm like, wait a second. The obvious thing about this is, yeah, because you do joule over c squared. Oh, look, we get our same number. We're getting the kilograms out because we're taking the c squared out. All right. And again, if you do 1 over c squared, like basically Rick was saying in the notation there, it's good to identify ones. That's what I'm going to claim is probably a really smart thing to do. Are there points of oneness, or at least within the system and the units that we're using? Is there an essence of a 1? Because if we can actually find the 1 things, then maybe we can use those as, like, I don't know, nav points, markers to try to actually map out the territory the best we can. I mean, if you didn't have any wayward markers, it kind of would have been hard to be like, oh, let's make any type of map. You need to have some references, right? Okay. Well, the thing that got me really giddy is that whole, wait a second, we just had a joule over c squared here. We get that mass. We get a joule over c squared here. So we're getting out that mass term. And let me make this prettier for y'all, because everyone deserves it, and it helps my mind work. Okay. So we've done a video on this before. I think it's, was it the vacuum energy thing? It was like probably the last video posted on the channel. But basically, what do we have here? All right. So we're taking the relativistic mass of 1 joule. And really just dividing it by c squared to get the mass out. Okay. So this is a mass term over here. It's basically that 10 to the negative 17. And we're setting it equal to the geometric mean of the Planck mass. And then, since it's a geometric mean, we're taking a square root. We're using 2 terms with kilograms in it. Okay. And we want to solve for x. And the factor that seems to be the best fit for the different versions, that seems to be the simplest, that some dude like me might be able to start to interpret, is you divide that whole thing within our root form by pi divided by 3. Yes. Pi divided by 3 happens to be the term. And we get this out, and you can add your meters cubed in there, but that clutters it up. But you double check, and we're solving for kilograms here. All right, so we got kilograms, that number. We do our energy conversion. We do our E equals mc squared right there. Bada boom, gives us this 5.3535 times 10 to the minus 10 joules. 3.34, yada, yada, giga-electron volts. So, oh, and since that's in energy, if we divide by meters cubed, that would make it a volumetric term, or an energy density term, pardon. And Oh, look, we're in the magnitude of the universe vacuum energy density. And then if we go over to our friend, what is it? Cause logic. Oh my God. Can't call constant. Something like that. I think it's. Is it within this guy? Let's see. No. Where was it? It was, there we go. Okay. So over here, ooh, I think they've updated some of this. Groovy. All right. So according to the standard Lambda CDM model, standard yada yada. So basically our numbers are here. The vacuum energy density, rho vac. I've been saying that totally wrong before. Why? Because I saw a P, but that's technically rho. Why? Because we got the P out. It's equal to negative P vac. It's 5.96 times 10 to the minus 27 kilograms divided by meters. Wait, what was the term we got out? Oh, 5.9566 times 10 to the negative 27. We were solving for kilograms. All right. If we go over to the other conversion, about 3.35 GeV per cubic meter. And we get the equivalent is, I'll go back. There we go, C squared. All right. Oh, look, 3.3414 giga-electron volts. All right. I mean, again, might just be a little coincidence, but we got something with pi and 3 in there. I think those might be useful things that we can use to help parse what might be going on. So we've got that over there. It's not the bonus commenting. It's not the length of the Planck. It's how you use it. Well, both of those things might be very significant. I guess we're gonna have to see. But all right, I find it interesting that we seem to literally be able to use these same operations again and again, and they keep popping out again and again. It's like, all right, let's look at a relationship. All right, let's square it. Let's see what happens. And again, I'm sure people knew that, but I'm like, wait a second. The standard C squared energy conversion rate is literally this term we set it equal to, or at least using that method to determine the vacuum energy density. By taking a geometric mean between two numbers, and within that mean, dividing it by pi divided by 3. I don't know. I'm simply conjecturing here right now. I don't know. Does that have anything to add, or?
I mean, the constants of nature.
Hold on. Let me adjust. So let me just change my audio thingy. Oh, we are on the MacBook microphone. People can actually hear you. Cool.
The constants of nature are first and foremost a conversation of how the bases fit together anyway. And a joule is just a bunch of the bases, right?
Yeah.
So, I mean, the ones in the system are the big surprises to get used to, because, I don't know, we're used to ignoring ones, but we're also not used to imagining physics as a physical structure. Maybe, I mean, some people it might be, but, you know, I guess, so the point maybe is that I'm excited about here is the structure you're talking about here. We're taking physical relationships in nature, right, and seeing something pop out. But that thing has a relationship to the joule, right? The joule itself is just a composite of units of the different dimensions. So the units themselves are the things that we're revealing the relationships of in general. So it's surprising maybe when you get a composite one that you'd be familiar with, but it's pulling out joules on purpose, because the joules are part of the system. Joules aren't a random unit of energy made up by some person and we just started using it.
Right.
It's a unit that's coherent to exactly the structure of the constants of nature. So anyway, all the 5 dimensions and the composite uses of those dimensions are exactly that. Any other base or any other measure of something that's not one of those coherent systems is one that's just random and someone made up and maybe found useful for something, but they haven't made it coherent with actually the structure of quantum mechanics and general relativity. Nature.
Well, that's the thing, because a lot of times I think a lot of folks, we focus very on specialization nowadays. Because even when I was going to school for business and everything, it's like, no, you specialize. Why? That's where you make your money and everything. Yeah, you could be a standard practicing physician, pediatrician. Yeah, you can make a good living. When you go, they bring a brain surgeon or do plastic surgery, and you make a lot more money and stuff too. So it's like, all right, we incentivize people to do that. I think the only problem that might happen is if you're so specialized, and again, not all, but some folks, you got blinders on. You got blinders on. And if that's your task, that's fine. You're going to be an expert as much as you can based upon the information that you're getting there. But if you're trying to look at an entire system, you might need a very much broader view. And I know we were watching that video from Fractal Woman earlier, because she's kind of doing what you've basically been doing for the past number of years now, is going through NIST and the CODATA database, and she's trying to simplify it.
That's exciting to see, right? So the next thing she's going to discover, I'm predicting, is that when she's trying to find the commonalities in the concepts of nature, it looks like, right? She's trying to get her X system out of that. So when she does that, she finds all the combinations that she can put things together, this one divided by this one and so on, and tries them all. She'll find lots of things pop up, and lots of things get the same numbers for the first 5, 6, 7 significant digits, but then they change. So she's picking ones right now that don't have any divergence at all. All the digits work. And then she's going to find a lot more that have things that work for the first 7, right? So there's going to be something that goes off, and then she's going to be interested, well, how can I skew that 1 times 10 to the negative 7 number? How do I find the range in which all of the ways that get skewed minimized, right? That's like 2 steps of logic. But it takes a long time to come to those 2 steps, because you have to analyze all the data points first before you even can. So anyway, that's my prediction. It's exciting to see somebody else trying to do the same thing she's looking for a pattern in the constants of nature, right? That's the most exciting puzzle to try to unravel. That's the most rewarding place to find something to begin with, because when you find the structure there, your mind's eye becomes open to something new that you didn't have before. So anyway, that's the best place to look. If you look in video games, if you look in markets, if you look in made-up stories that are there to entertain you, that's a completely different thing. You're just going to get whatever Easter egg that was put there for you. Right. But if you look for the pattern hidden in nature, and this is the only time in history where we could look at this level, because we have things like CERN and all that list of CODATA for the actual measurements from all the best scientists at the best lab around the world over time. Right? Like that literally is the whole point. We collect the best measurements, and not just one, but all of them around all the labs of people trying to make these measurements. We get these data points that are way higher than, say, when Newton was around. What was the speed of light known to when Newton was around?
Oh, we
almost 1 significant digit.
Well, technically, for most of the speed of light, we've known it to almost 0 significant digits.
Yeah, exactly. So now we have so much more precision of the features we're talking about, right? This number of digits and error bars, the size of error bars, tells you the precision, how well you know the thing you're looking into. And the concepts of nature now we know extremely well. I mean, as a mathematician, you might think, oh, only 14 significant digits. That's not much. I'm used to thinking of millions.
That's not an infinite limit.
Yeah, but when you think about what that means in physical reality, like try to draw a circle. Just pick any size circle that's drawable by you, right? Or maybe you want to get a more exact circle, so have it printed out by a computer. And now you want to take a string and mark off the distance on the string and try to measure the distance of the circumference of the circle and the diameter. Try to just make a measurement. Okay, you're trying to see how accurate you can be with the best of your ability to measure and see and manipulate the world. And just see how close you can get to pi. How many significant digits can you get? And if you're thinking you're going to get well beyond 14, you're going to be very, very surprised.
It's I think, what was it? I forget what state, but for a while they had pi literally, like they ruled it as 3 or something like that. Somebody did something crazy like that. Yeah.
In the Bible, it's approximated as 3.
No, this was a much more recent time within the past 100 years, and they made it a law. It's like well, that was the thing. It's if you want to just use that for your roughshod and that works for whatever industry you're in, that's one thing. But if you're literally trying to do precision things or mathematics, you would say that might be one of the most precise things that there could be. Yeah. The one significant addition is not going to cut it.
This is like, if you think of multi-layer chess, it requires you to abstract the possible moves one layer deeper, right? Mm-hmm. Well, looking into these concepts of nature are pretty much the most layered of abstraction of a puzzle that you can solve, that there is definitely a solution for. Anyway, the abstraction is why it's difficult. So you have to be able to abstract, but you have to be able to conceive or put together ideas that work well together and understand the parameters in which they work well and not work well together, right? Anyway, the abstractions here are all difficult because we're making ourselves suspend what the thing is that we're in relationship with, right? What is the Planck length? What is the Planck time? Oh, well, let's look at the relationship, talk about that. Okay, but what's the thing we were talking about to begin with? But we're doing that, why? Because we don't know what they are. Right. We're trying to find all the relationships so we can then say, what are the things that we're talking about that have those relationships? That's the whole point. Anyway, I'm ranting.
Oh, no, that was a fantabulous rant. But it was one of those things where that's what I was saying, because that was one of the things that you had first taught me when I had first interviewed you the original time, is that it's like, what is one? And it's like, all right, well, one is not a prime because number file told me that about 2 hours ago. So I'm just appealing to authority and everything. It's like, well, it could be the 0th prime. It's literally next successor. And maybe that complicates some ring theory, or maybe it doesn't, if you consider it that way. Who
does that video on one?
Oh my God, I don't.
That's a fantastic.
It goes into all the relations. One. It's literally
without letting you know it's one until the very end, right? Anyway.
It's like the inverse square hole girl.
So there's a big mystery there that's parallel to the mystery of one, right? If you try to imagine any possible universe, because you're trying to be able to conceive a universe that has properties and eventually explain our universe, but you want to get to the first stage of any.
Yeah.
Okay. Like you might think the simplest thing might just be something going around in a circle, and we'll call that a universe. There's nothing else. There's just a circle. And then you think, wait, how can I make just the thing going around a circle? Oh. Okay, I can't do that.
So where are you creating said circle?
Yeah, the concept of the simplest thing that can be made, and then after it's made, it continues being, so it persists, right? Is a really difficult abstraction to begin with. Okay, but these are the parameters of whatever that thing is.
And so you use the clues and everything. You follow the evidence. You see where it goes. Maybe the evidence, maybe there's nothing there. At least based upon the time I've spent here at the monastery, there seems to be a there. Maybe not everything. Maybe we've gone off. Maybe we need to recalibrate.
Or maybe we fail to conceive what that pattern meant, right, as we go. But the more time you spend investing in it, the more your brain can actually put it together. So it's working, it seems.
Well, that's the thing. It's just because it's like, and now a lot of these things, it's like, I know people have known about stuff like this, but it's like for me coming basically almost like from like the outside, literally just like a lot of folks right now, just watching on the internet, just because I'm interested in this stuff and what might be going on. And just going through and just being like, noticing this relationship. And then watching Fractal Woman probably about 2 or 3 months ago, she had something with John McInerney or something like that. I apologize, sir. But he's a physicist, and he had pointed this out to her. It's, you just, for the fine structure constant, you can just take elementary charge over the Planck charge, have the whole thing squared. She's like, that's very fascinating, because that's what it comes out to. I mean, just going through the calculation, I'm like, what the heck is 4 pi h bar c e naught? I'm like, okay, there's a whole bunch of wish-washing and dimensionals and something in a sphere going on.
Much simpler, yeah.
Yeah, and I just like, wait a second. I look at the number. I'm like, all right, something to the negative 36 power. I'm like, wait a second. This number looks a little familiar. Let me take the square root. Oh, because it's giving us a dimensionless number and it's over charge squared. Maybe it's charge squared.
Yeah. So I'm not sure how public the mystery of the fine structure constant is in the lexicon today of people, but I think this might reveal it to some who didn't get the mystery there. We have the thing in the world of charge, right? Mm-hmm. Electron charge or proton charge, but it's the same thing. Right. So the thing that shows up with charge in the world, electron charge, divided by the mysterious boundary of charge we get from the constants of nature, right? We find it from there. So these are like two natural expressions of charge. Why are they natural? Because they're the ones that show up.
Right.
But the two of them compared to each other squared equals this fine structure constant. Now, it shows up littered in connections between most of the constants of nature. So it's a very, very central piece of what's going on. But we're just talking about this ratio squared, the same ratio, the same type of ratio he's doing here. Anyway, it's fun. It's fun to explore all the little things, even if you don't know what it means that you're looking at. You go step by step and try to.
That's the thing. That's why I like doing these, just because I can go through, and then different people are commenting and everything here, and then somebody will just say a term, and it's like I never heard that before. So maybe I go look at it either during or after, and it's like, oh my god, I haven't even explored any of that stuff before. But
there's so much math. Thank goodness.
WWK, yeah. WWK is commenting. Most interesting thing is one, that it doesn't exist unless you have a notion of two. That's interesting. Maybe you need a notion of -1. What happens if -1 was primal? Because people say, oh, quantum mechanics, we need to get there through the square root of -1. That is primal, or that's what's really going on. It's like, okay, if that's true, does that mean that -1 is more elementary than 1?
But he still has another scaling issue he's pointing out, that even if you picked the 1 and the 0, you still have any scale comparison for the next step. So
you need to have the relationship. Very good, very good. No, I was thinking as a one establishment or something like that. Well, that's very interesting. You can look at it in the different ways there. But it's and even just when we take the square off of that elementary charge over the Planck charge over here and stuff, we get our Joule 1 and everything, or they I believe it's considered an amplitude of the fine structure constant over there. So, but again, I think it's interesting because you can take all that and then you just do over here. You just go. Let's do this. I'll just do Joule over C squared. Okay. There was no point for me putting it over there. It's just not be lazy and kneel down. All right. If we do this, we do our friend over here. We can just do 1 joule. I'll do it this. Let's do it. We'll do it this way. It's more familiar. Joule over C squared. Oh, kitten supervisor. There we go. All right, so we got Joule over C squared. We can just do our little thing here. And then we got, let's get Planck mass. And then we just multiply it by, solve it, multiply. Solving for X kilograms. That whole thing divide by 3, I will claim is equal to the evac. I didn't put in the meters cubed in there just because it gets a little messier. I think this is prettier. So the energy of the vacuum, aka it's 5.9566 kg times 10 to the minus 27. I have that number in my head just because I've looked at it so dang much. So I literally looked at it right before there. Okay, so you get that. Basically, the measured and calculated value estimate right now, according to the Planck 2015 survey, is, or maybe the 2018 update, it was the same 3-year period before the satellite was no longer operational, was 5.96. So I'm like, all right, I would say it's got about about 3 significant digits there. How's our confidence? Oh, they were only listing 3 significant digits there. So I figure it's probably not a bad educated guess there because, well, we have a geometric mean. Apparently those are very important there. We're just solving for this to get that. And then within that root mean, we've got pi divided by 3. I'm like, okay, I think they use a 3 in there because I think they calculate via like the Hubble constant and stuff. And then I think it was at the A naught or 3, or they're dividing by like the 3 spatial dimensions in there. I mean, I really should have spent far more time on this, but get pulled into other Wolfram holes and stuff too. And I'm like, there's a bunch of smart people that already know that. So let me just shut up and do some calculations for a little bit.
The answer here is going to be times kilograms or in
yeah.
kilograms?
Sorry. It's
in
kilograms. I'm listing it in
Okay.
kilograms. We're solving for kilograms. That's why I'm expressing that.
So this whole thing is this top right here. Okay.
Yeah. I should probably. Yes.
Okay.
The problem when you're a very messy writer and I didn't take up the extra 2 feet that was over there.
But then we end up with kilograms and kilograms squared. So we square root, we end up with one.
We end up with 1 dimension of mass there. And you can do this, you can just do
and this is I like, so whenever I say pi over 3, I'll think of the angle pi over 3. I'll try to think of many ways to represent it. But this one's suspiciously also 2 pi over 6. Right? So some cycle somewhere, a unit cycle.
Is that
divided into
squared
6
or something?
Circle divided into 6 is the structure we start with the imaginary golden ratio. Anyway.
Hold on. Say that again. Say that again.
So you can rewrite this as 2 pi over 6, right?
Yes.
Yeah.
Oh.
And what is 2 pi over 6? You can think of it as a circle divided into 6 ways.
Oh, that's
which is exactly what our imaginary golden ratio does. Right? In the structure we started with. So you're just saying you think this structure here is rooted right at the throat of the connection that we made.
But the imaginary golden ratio is built into like the gamma function too.
Yeah.
That's the difference between gamma 1 and gamma 2.
Yeah.
Or the W1 and
anyway,
W2.
that's to me an easier way to interpret what's happening there. There's every way you can interpret it would be correct. But I mean, if it's correct.
No. Like I said, it's a claim. It's just we're doing a similar because I originally was trying to do this, and I'm like, because I had that calculation that it's acclaimed again explanation for why the Higgs boson mass has the Higgs boson mass. I was just trying to find another route to verify this. You can do this, but if you plug in that, it ends up being the Higgs boson ends up using this method. It comes out to be about just under 126 GeV. So I'm like, that seems to be too many sigmas away from the current things there. I mean, maybe we're underestimating it. Maybe that's a thing. But the next thing I noticed, I'm like, oh, look, it looks to be about 2 pi joule seconds or something like that. I'm like, well, what if I arrange this? What if I put this in here? Did searching. And then I was like, wait a second, best fit seems to be pi over 3. And I thought I was taking outside the square root.
I think it's a beautiful one.
I just put it inside the square root and then ended up
Of course, we keep in mind since it only has 3 significant digits.
Right, our confidence
we're not going to build much on it confident-wise yet. But it's a nice thing to notice as a symmetric connection because you can easily interpret what it says.
Oh, that's the thing. It's like, once you look at it, it's like, all right, you play around on a Mathematica notebook or Wolfram Alpha for like an hour or so. It's like, you go through and it took me probably about a week or so and I didn't even come up with the 2 pi until you had mentioned that right now. But you just look at it, it's like, realistically, how long does it take to type in Joule C2, blah, 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 blah. It's like, no, this isn't very long.
If you're not used to using Wolfram Alpha, you wouldn't expect this to do anything for you.
Yeah. I was just trying to find something else. I didn't find what I was looking for, and I found something more interesting. So, or at least allegedly, something more interesting, and again, could be totally wrong, but it happens to be getting the magnitude seems to be matching the significant digits that we have confidence in. Is there something there? Maybe. But hey, again, as a gamer, I'm just looking at like, what are the superpowers? Like, what are all right, we've got stuff, it's doing things. All right, we got the stuff. Joule, energy. We're divided by c squared. Why? Because we want to get the kg out. Kilograms. All right. Why? Because we want to solve for kilograms. All right. So we're using a geometric mean. Apparently that's very important because it shows some form of, is harmonic the right word or no? There's a harmonic mean. That's something else.
That's another thing.
Okay. But the geometric mean is you're taking two things, you're multiplying them together, and then you're taking the root of the X number of multiples within the thing out. And the only thing you need to adapt is basically throw like a pi divided by something term in there. And then you happen to get out of the magnitude, the first few digits. And I'm like, all right. So a circle, something curvature, and it's some notion of division going on. We're getting it out. It seems to equal it. What does it mean? Well, it's a geometric mean. It appears to, and again, I think I'm stealing part of this from Dr. Sabina Hostenfelder, was something about the vacuum energy density being about the curvature of free space or something. So I'm like, well, that's what I'm trying to calculate for. We're trying to calculate the energy of the vacuum, or technically rho vac, and then p vac is the minus version of it. You just divide it by meters cubed. So you're putting it in a cubic meter, and that's the approximate energy density per cubic meter there. I know, fascinating stuff. Oh, hey, Sudo. How are we doing, my friend? Thank you for joining over there. That's this on the, let's see what else we got going on. Oh, I've got a little bit of a rant here. Let's see. WWKK is saying it's a great thing that SI unit tried to hijack the notion of electron volt by writing it in terms of joules. It's, oh, well, thank you, my friend. It's very enlightening. I stand by the unreasonable effectiveness of electron volts, because when you go to the page and you look up electron volts, it'll be like have electron volts and then have it in coordination with meters. This is an energy, so you can convert it to mass or a mass equivalence and everything, and you can add Boltzmann's constant and get a notion of temperature and everything out. It's very fun. It's fuzzy helper. Yeah. Kitten has been helping with discoveries. Yeah.
The kitten goes round, round, round. The kitten goes round.
But so it's just very interesting that it's like, again, you start off, oh, you okay, buddy? But oh, yeah. But you see things where it's like,
now he's
I listen. Oh, okay. Yeah, now he's he's gonna get you. Oh, he's gonna get you. Oh, you end your centrifugal force. Okay. But I just find it interesting because I just start off, I'm like, all right, I give burnout from politics, all this and everything. A lot of people hate each other. We could legalize dueling, or I could try to spend my time doing something more constructive, maybe something like this. But I remember listening to Professor Sean Carroll, and it's like, oh, in physics and stuff, you look at relations between different things. And then if you need to, you square it, you square root it, you do these things. And he just lays out so casually. And I'm like, wow, this man is a wizard. And then I'm going on. And then once I finally like pop my proverbial cherry, so to speak, apologize for the misogyny, but you're going through and it's like, wait a second. This does seem to hold. What happens if I look at this relationship? I'm like, wait a second. That's easier to understand the fine structure constant from like, I don't know, two things squared equaling alpha versus you got a thing squared. And you got 4 pi h bar c e naught. It's like, what does that mean? Charge squared, apparently. Why do they write it that way? Because that's the way we write it and we have it defined. And if you can find a little pocket of computational reducibility in there, okay, that should help, no? At least that's what one would think. It's kind of like a kid being a scientist and being like, what's going on? Why is my heated spot no longer warm? Well, maybe because there's some smoke and we're trying to keep the smoke detector from going off. So we're opening up a door. We're opening up a door over here. There's an air current and everything going through. And then he starts to get chilly. And he looks down at the heater by his feet. He's like, why aren't you working? And then we realize, oh, okay, you don't like the sirens any more than we do. So we close the doors, and then he becomes a hot little pelted pat of melted butter.
Yeah.
So let's see what else we got there. All right. So, all right, we covered apparently why we got a Joule there. Very interesting little building block relationship that you can do there because, well, if you just do your standard, C squared, whatever, your mass, you get mass equals energy, yada, yada. Yeah. We're claiming energy over there. I don't know. I feel like, damn. I thought I may have had some actual extra connection there. I'm like, I'm writing something out. I feel like I should
So you're doing the
say
same.
something.
Energy is joules.
Yeah.
Bring it down here. Energy over C squared is mass.
Yeah.
Mass. Yeah.
Yeah. Yeah, but it's a cool little thing. But then it's like, all right, well, maybe again, just coincidences and stuff. But I'm like, well, it does seem to, at least for me, be able to give extra information because apparently we got this formation over there. And we do this guy over here, which is, we do, which one was this? Like mass over mass of the Higgs. We square that thing, H bar, we set it equal to 1 joule second, not divide by second. So on joule seconds, we're basically, if we solve for, same thing, basically we just solve for X kilograms here. Whoa. Okay.
Sorry, buddy.
Okay.
But let's get too fun.
Got that?
Yeah.
Is that equals, and then basically just mass of the Higgs because that's what it computes out to. All right, let's see. Oh, Rick is commenting, 4 pi steradians is the solid angle subtended by a sphere. When you see 4 pi, think all directions. I mean, that sounds right. Or at least within that realm, whatever magnitude we're talking about, unless we think about it differently, but that's generally how I think about it. What else we have? Let's see. WWKK is also commenting, it's a bit of a scandal that you write surface area of a sphere is 4 pi squared, but you could have equally written circumference squared. Ooh. Maybe that's where the Pythagorean triple for. No, I think that's.
He's got a good point. It is a scandal. Everyone should really stop and pay attention to. Wait, what? Why is that the same? Yeah.
Because its circumference is going to be whatever x pi. Well, the ratio is going to be pi, and then you're going to have whatever it is, and then you square that. Hold on. Okay, this is why we're here. My noggin is a jogging. Let's take a look at this. All right, share with the class. Boom. This guy. Let's go over here. From. Okay. So if we add a circumference, all right, we got 1. So all right, 2 pi. Yeah. So 2 pi would be a unit circle. Equals 4 pi squared. Oh. Yeah, that would end up just being one thing. Is this the unreasonable effectiveness of tau? Is this what it is? Because I feel like somebody maybe asked me a question before, and they were asking, what is the simplest thing you might be able to boil it down to? And my initial response was just thinking tau. Because you want to say pi, you want to say 2 pi, and I'm like, well, no, that's another 2 things together. Is tau the way to go? I think Fractal Woman has also brought that up because she's usually thinking about things as cycles per second, or that's the main bit of her jive, to my knowledge. But Pi never gives you a straight answer. By Pi.
He's always irrational.
Yeah, always irrational. Pi times d to the pi times d squared. Yeah, d is the die. See, okay. See, that's one of those things, because at least when I originally got taught that stuff, they started going around and it'd be like, all right, here's the diameter of our pi. But now we're going to divide it in half, and now you're just going to have to do 2 pi. It's like, why didn't we just do this? Why? Because we like 2 pi. To be fair, I'm never really going to argue against more pi. I mean, personally, I am pro pi. It's personal opinion. Fizz may agree with me on that. Just don't eat too much cheese pie. Cheese pie? What are you talking about? It's cheesecake, you fool. Well, certain places may disagree. Is that like the reason why in the UK they classify biscuits and cookies as different things, because one would have more sugar than the other? I know there's like some reverse thing where we consider like chips are French fries over there, but then our chips over here, no, they're potato chips. Why? They're extra thin, extra crispy, and everything like that. And I don't know, communication can be hard, but oh God. So let's see. How can we okay, we won't embarrass Fizz too much right now. There are other days for that. But what else we got? Cheesecake. Yes, the cheesecake. They cheated. Well, I can't say they cheated. Maybe creative use of game mechanics there. But let me see. We had that. Oh, I'm sitting in front of the stuff that I just wrote on the board because I am a terrible person. All right, so the whole thingy over there is just to express that. Oh God, it's blocked by the shininess of the light.
Move it forward. Yeah.
There we go. Forward. There we go. We're limited a little bit by chord range. Okay. We'll go this way. All right. Okay. Now. Okay. Now we're only blocking the P a little bit. There we go. That's better. There we go. The whole point is, all right, we get a relationship between 2 dimensionally meaningful things squared. Oh, we get the mass equivalent of 1 joule, basically our C squared conversion factor. All right. We get elementary charge, divide by Planck charge, or boundary of charge, we square that. Oh, we get the fine structure constant. Cool. All right. If we take the Planck mass, we're solving for X kilograms because we're trying to figure out the mass of the Higgs. We have to put it to the magnitude of h bar, and we set equal to 1 joule second. Claim is you get the mass of the Higgs to at least 3 sigma of the current Atlas world average measurements, and like 0.2 sigma from the 2022 CMS experiment measurements there. So it seems to be within our error bars and stuff there. And I don't know, I want to buy muon collider. I think that would be a pretty cool thing, just so we could get some extra precision. And again, maybe there's nothing there, but I'm just get the magnitude in at least the first couple of digits. And then we got our little thing for another claim, the energy. Well, at least that is what it is, and that is basically what it is defined as over there. So I mean, you can say, okay, that's a speculative calculation. I just get digits. This is a speculative calculation. Basically, a joule over c squared. You just do it as joule, and we could just do the Planck energy and just solve for like xGeV over there. And take this geometric mean. We got a circle. We're dividing this whole geometric mean within its root by a circle, and we're dividing that circle into 6 pieces. Bada boom, bada bing. We get the claimed energy of the vacuum, aka 5.95 yada yada times 10 to the negative 27 kilograms, or 3.341 GeV per cubic meter. If we threw our cubic meter dimensions in there, I just leave them out just because it usually just clutters the notation and stuff, and it ends up coming out to be the same, so you can throw it on after. But biscuits are crackers. Okay. Potatoes can cheer us up, especially when the chips are down. Well, like a lot of folks might agree with that, Rick. But all right, this is fun. Gotta look into some other things. Gotta get some neurons going in ways that I haven't in a while. Let's see. That's about all I have. Questions were asked earlier on. I apologize. My car is still currently dead. Should find out more tomorrow, because as somebody that had recently been through putting a new engine into that vehicle, I figure I'm not going to have my car for like 2 months. So I got to go down tomorrow and see if they're going to comp me some plane tickets so I can get back for Christmas, rather than missing Thanksgiving and Christmas that I plan to go back and see people on the East Coast for. I'm sure they'll be very accommodating, because they're good people. That's what we need to keep telling ourselves, right? No, I think most folks are good people. It's usually people that stir the pot, that like myself, all us terrible people starting fights on Twitter and the internet and disagreeing with people and totally not pointing out hypocrisy, including ourselves, but that's okay. Right, Geishel. Oh, wait, no, I already said that. God, that was in the past. I'm like, wait a second, those words came out of my mouth earlier, didn't they? But let's see. Is there anything else fun? Oh, we can do maybe this real quick. No, we'll save that tomorrow. What else could we be doing? I really just need to finish. I opened back up the paper I've been procrastinating on. I'm just writing up the thing for the Higgs right now. And we'll submit that to the Wolfram Complexity Journal, because I know at least somebody will look at it and submit it to like Physical Review, wherever. All the little places, any place I will submit to, I will submit to. They are free to never contact me about any of these things. Worst case scenario. Or apparently the best case scenario, maybe they approach you and then they say, all right, for a low publishing fee of $15,000, maybe we'll put it in there. Now, not all, but at least of the grapevine, apparently that's a thing. I'm like, hold on, wait, pause for a second. So what you're saying is some of, at least has been claimed, I haven't experienced this personally, some of the most renowned journals that charge buttloads of money for people to access them in order to have your work be published in a high standard peer-reviewed journal for other people to see and cite. You got to pay to play? That doesn't seem very academic. Okay, now I'm just being pessimistic and starting to rant here. Yes, with all my time on the internet, people talk all about different colors and everything, but it seems like the only color, when you boil it all down, that matters is green. I ain't saying money is the root of all evil. I think it really is good at watering things and getting people to be incentivized to do things that they may not do if they could survive in a, I don't know, true post-scarcity society there. But yeah. Oh yeah, no, got to be careful, Wyoming and everything. Yeah, I'll probably just end up flying back. Yeah, that's what it's looking like right now. So I should probably get plane tickets this week. so I can at least have a time to get in, and that'd probably be a minimal cost. I don't want to have to be like a 1-star review customer, because as long as they make it right, if they're not going to make it right, well, then it's like 1 star. I went into X oil change place for an oil change, a new battery, and got a seized motor. Why? Because that's what happened. Oh yeah, I was going back from the holidays. Oh, you could even escalate it even worse. To be fair, they were the last people that gave me my previous oil change before they replaced the engine the first time. I think those were from very different things, and I don't think it was out of oil. It was more like there'd probably been a leak in one of the radiator hoses and everything. It's like, oh, your engine's overheating. Oh, stop. Oh, drive to the dealership. Go, boom. Oh, put some stuff in. It's okay for a while. Throws a code. We need to replace your motor. Oh, that stinks. And then 2 months later, they eventually replaced it, and now we're going through it again. Why? Well, but Rick, I think I don't know if you're around. I might give you a call tomorrow. But oh no, that's oh no, storms are terrifying. All of a sudden, it's like oh, we lose like 100 feet altitude. Why? Oh, currents, this, that. It's hydrodynamics are a fascinating thing, my friend. But yeah, all right. I've hit the hour mark. I'm just rambling now, but stay tuned to tomorrow, where we may look at some frequency, and our friend Pi may make another appearance. But until then, take care of yourselves. Peace out, everybody.